So we saw in the plot showing the solution for a given optical parameter set that the extinction and the absorption and scattering behavior is very complex, and this is very frequently too complex to solve this in detail every time. So we are looking now at an approximation, the so-called Henyey-Greenstein approximation, that describes the scattering by 3 parameters. So we have the extinction cross-section, we have the albedo omega, and we have the average scattering angle, so the mean cosine theta. This is the G parameter. So for an example, if G is 0, we have isotropic scattering. If G is 1, we have pure forward scattering, because G of 1 means that the cosine, that theta is approximately 0, so forward. And the phase function proposed by Henyey and Greenstein is given here. And this can also be expressed in terms of Legendre polynomials, PL, as powers of G. So we have here this series where the phase function in every angle can be described by this. And we find, and this can be tabulated because we only need for a certain dust distribution to find a good set of these 3 parameters, the albedo omega, here we have the G term, and we have the extinction cross-section here. And so we see that this can be described nicely here. So again, these 3 terms makes it convenient because it's easy to implement, for example, these Legendre expansion in computer code, and then compute the phase function for the scattering. So for the radiative transfer, this is frequently done, and the general case is that we need to consider the scattering within the general emission coefficient epsilon, where we now implement the cosine theta as mu. So we have a directionally dependent coefficient, emission coefficient, which is the albedo over 4 pi. And then we integrate over all directions, so over the full solid angle omega prime. Have here the phase function mu minus mu prime. So this is integrating over all scattering angles using the phase function from the previous slide. So we can compute the intensity now as a function of the frequency or wavelength and a function of the direction in terms of Legendre polynomials. This has been done for different geometries, for example by Flannery, Roberge and Rybicki in 1980, that show that the decay of the intensity into a cloud is shallower than exponential. So when we only have pure attenuation, which is because of the scattering. Okay, So here on this slide, we see the results of the radiative transfer penetrating a plane parallel slab of gas and penetrating a spherical object, here given by the top and the bottom row in the figure. This is a function of the G parameter, which is here isotropic on the left hand side and mostly forward on the right hand side. And we note that for the same albedo, that the intensity in the isotropic scattering case is lower than in the more forward scattered case, and the reason for this is that when we are at a certain point here, the radiation coming, the total number of photons is basically given, of course, by all the photons that are penetrating along this line of sight and still reaching this point, so that are not scattered away and not attenuated, plus those where we hit a particle and then are scattered into this location. And this is stronger here in the case of the forward scattering compared to the backward or to the isotropic scattering, because in the case of isotropic scattering, at every point radiation can also be scattered in the opposite direction. So in total, the number of photons that from the left hand side are scattered into this point is smaller compared to the more forward scattered case. So overall the intensity here needs to be lower in this example, for example, compared to this. Okay. When you look at this in more detail, you can also compute the intensity not outside of the scattered particle or the effect of a multitude of scattering particles, but also within a scattering particle, here a spherical object. And in this figure, I show you the intensity of the E field in the scattering particle, given on the left hand side as computed by the Mie theory, in the middle panel here by doing ray tracing by using here 60 and 2000 rays to show you that the result is equivalent. If you look here at the shape, this looks similar. Also here the different intensity distributions.